So let then start today's lecture. So and we are almost toward the end of our lecture series. So let me recall what we have done in the previous day. So in the previous lectures, what we have seen that we have done a deterministic differential equation. Through that differential equation, we seen how can one how can one captures the basic essence of evolutions, basic essence of selection, natural selection through a dynamical equation, and that equation is known as replicator dynamics. And that equation basically nothing but that captures truly captures the essence of Darwinian selection, that says that in a population a frequency will increase or decrease with time if it fitness if that type fitness is larger than the average fitness of the population. If some behavior's frequency will increase in the population if that behavior fitness is larger than the average fitness of the population. So this is the replicated equation. Now opposite of that, in to write this equation, we assume one assumption, that is the population itself is infinitely large. There is large number of individuals are there, they are reproducing, and that's why we can write this kind of equation. But in principle, if the population is finite, then in place of this equation we should write this kind of equation. So this will be x dot and some x into fx minus phi plus some noise terms would be there with some strength of the noise sigma, and some this is the noise term. So this kind of equation should written there uh, in place of that deterministic equation, but we don't want to go to there. But you should know that in finite population that deterministic equation does not work. Then what should we do? We develop a stochastic version of the selection that will do our job. So let us, what we have did, we introduce the what is called neutral dip. Neutral dip means if there is no selection, the question is whether or not one type of behavior at the end of the day will fixate in the population or not. This is the concept of neutral dip. So it is called that there is no selection at all, but only because of randomness, only because of random birth and death process, one type of individuals uh, eventually eventually takes over whole the population. And we introduce the concept of the Moron process, where Moron process means it is very important concept in game theory, in finite population game theory. In everywhere, whenever you want to deal with finite population birth death process, Moron process is one of the way to model the birth death process of a finite population. Now, how the finiteness of the population uh, we uh, fix the finite, we means we sure that the population remain finite. So that is the process of Moron process. So we have ensured that the finiteness of the population by saying that if one individual taking birth, and simultaneously we have to kill one individual, or that individual which is taking birth will replace some other individual from the population. So that is the Moron process. So one individual will take birth, and that newborn individual will replace another individual from the population. That's why the total number of population will remain fixed. Now we have seen that what could the random drift done. So random, from because of random drift it could happen. So because of random drift, since there is no internal because of random drift, the population could either go population state. Suppose there are I number of individual, a type of individual in the population. So this boundary is corresponding to I equal to n, and this boundary is corresponding to I equal to 0. Now suppose population is starting from any state here, I equal to suppose n by 2. Now, because of birth and death process, in if I want to generate its time, I want to generate its time sequence, what will happen? Sometimes maybe it will increase by one step, and sometime it will decrease by one step, and here it will increase or decrease. In this manner, it will either touch this boundary, and after it touches this boundary, since there is no mutation, that means only A type individual produces A type individual, and B type individual produces B type individuals. When it hit all A type individuals, then from there is no point of return. Their population will remain there forever, because all A type individual will produce A type individuals. This could be one case, and another case could be that similarly, one could be birth death one. So from this, so one could process like that, and it could hit the I equal to 0 boundary. I equal to 0 boundary means no A is present there, that means all B, and it is these two state is called the absorbing state of the population. If the population, because of this stochasticness, and there is two absorbing boundary condition, then we know that, so we know for sure that population cannot be there for mixer state, or the population of A type and B type cannot coexist it. But at the end of the day, you will see either all A type individuals or either all B type individuals. So that is the effect of the stochastic process or natural birth death process. Now, if there is no selection, that means that lineage.
But I have a query here that we have seen that since ages, the many species have coexisted
Huh,
altogether.
exactly, coexisted together. So that means that thing is not modeled by the stochastic model. This is very simple model, and we cannot say from this model that there means this model can certainly cannot say the coexistence. We cannot conclude from this model the coexistence. We can only conclude that whether all A type individual will be there in the population, or all B type individual will be there in the population. Why? This is very simple model, and if you want to see those type of thing, then you have to consider the realistic situation that this is not the case. There will be some mutation. So some A type individual can produce B type individual with some rate mu. It could happen. Then all A type individual will not remain absorbing state, and all B type individual will not remain no longer absorbing state, because all B type from all B type individuals, it could produce by mutation some A type individuals, and this process will means it could, you can see that the coexistence could be possible there.
Okay, so there must be some other advanced equations wherein the coexistence and co-evaluation would have been considered,
If
isn't
you
it?
introduce the mu, if you introduce that in the birth process, there is, suppose here, this is the only way to increase I to I plus 1. But if you in this, with this process, if you include some this process, suppose B replace, B is producing an A, and B with reproduction rate mu, and B is 1, I choose 1B to die. Then you see in this way also that I could change from number of A type individuals could change from I to I plus 1. So if you include with this term only, then you can actually model simple model, one simple model to whatever the coexistence is, means whatever model is needed for coexistence.
Okay, okay, okay.
So only mutation could help here. Now we don't want to see the what will be the effect of mutation, and this is the one thing. And we ask one question here: what will be the probability that, suppose there is n number of individual in a population, n number of individual in a population, Now, what is the probability of any one red individual take over whole population? And since there is no selection is going on, only the random chance, then we can argue that the everyone should have equal chance to take over the whole population, whether it red or blue, it doesn't matter. Everyone should have equal chance. If there are n number of individuals, then what is the chance of a particular red individual to take over the whole population? That should be 1 over n, because everyone should have the equal chance to take over the whole population. From that we know that the fixation probability of red individual in a blue individual is only 1 by n. And if there are I red individuals, everyone has a same chance to take over the whole population. That means what is the total probability of I type I number of A type individual takes the whole population, that will be simply I by n. So that result we come, that result we derived in the previous class. Then after that we have seen that the process from where we can calculate this I by n and x equal to I by n. Now we then shift our attention from where the birth rate and death rate is equal. If you see from here, the birth rate and death rate is exactly equal. Now we shift from there our attention that if the birth rate and death rate is different from one another, then what kind of fixation probability we expect? Fixation probability means if there are n number of A type individuals and some one type of B type individuals appear in the population by some mean, now what is the probability that this B type individual will take over the whole population? That probability is the called fixation probability of this B type in the population of A. And we have calculated that is nothing but x1 equal to 1 by 1 plus summation of this quantity and gamma k, and gamma k is nothing but the death rate of that B type individual, death rate of the B type individual by birth rate of that B type individual. So death rate of the B type individual and birth rate of the B type individual. So that's it. Now let's do one thing. If we introduce a constant selection in this random drift business, so random drift with constant selection. Random constant selection. Now suppose that there are again our favorite two type individuals are there in a population, A type and B type. Now there are many A type individuals, many B type individuals, many A type individuals, many B type individuals. Now suppose that the reproduction fitness of B type individual is 1, fitness of B type individual is 1, and the fitness of A type individual is R. Now fitness of A is R and fitness of B is 1. Now if R is greater than 1, then what can we say from this? That A has a higher fitness than B, and the fitness does not depend on the frequencies, it is a constant fitness or constant selection is going on. Now what about our previous dynamical equation suggests? So let's do it. So dynamic, suppose x is the frequency of A type individual in the population. That means in the population the frequency of A type individual is x, then the change of change in frequency of A type individual should be this equation Fa minus Fb. So this will equal to x into 1 minus x r minus 1. Now if r is greater than 1, then we know that since this term is positive, and x dot could achieve only two state, either x equal to 0 or x equal to 1, because these two are the fixed point. And we know that here, since the rate of increment is always positive, that means the x dot will always increase from any quantity, and if it always increase, then it could asymptotically reach to the limit x equal to 1. So that means x equal to 1 will be the stable fixed point, and that means at the end of the day, if the fitness of the Fa is larger than the fitness of the Fb, then all the individual of the population will become A type. Now the question is,
But I have a query here
hmm,
that I mean, what could be the meaning of the fixed fitness value? Because till
hmm,
now
hmm,
we used to compute this value. I mean,
by game theory.
based on yeah, by game theory.
Yeah, no, in the previous, yeah, constant selection means, suppose that A type individual reproduces another A type individual without interacting with any other individual. So game theory comes when we just want to model its reproduction as an interaction, that A type individual can reproduce another A type individual only if it interact with a B type individual or a A type individual. So then you will see that naturally, if I consider this interaction business, then I naturally see that frequency dependent selection. And if I don't want to model our reproduction by interaction, I just only want to say that A is reproducing A with a constant rate.
Yes, yes, yeah.
So that is the thing. Now here our deterministic equation says that at the end of the day, all individual in a population should become asymptotically all A type individuals. In the long run, we should not see any B type individual. Now, is it true that the probability of become fixed of A is always 1? So in deterministic case, that is what is suggesting. But let us see what stochastic birth rate process suggesting for a finite population. Then now we have to here we have to write the probability of birth rate, probability of birth and death. The probability of birth of I means, okay, let me write in this way. So if I randomly choose an A, and I ask what is the probability of birth, probability of reproduction. So if I choose randomly A, and what is the probability of reproduction A, that will be, since its fitness is Ri, now I plus n minus I. Now you will ask why I am writing this kind of function. So basically this is a and such. So there is no particularly reason why I am writing the reproduction probability in this way, that R is the reproduction rate of the FA, and and 1 is the reproduction rate is, okay, let me in this way, let me write in this way. So here what I is the number of A type individual in the population, and n minus I into 1 is the number of B type individual. Here R is the fitness, Fa is R, and 1 is the fitness of Fb. Now since the fitness is different for one another. Now that's why we have to retain down one probability for reproduction that should depend on the fitness, since there is a fit. Okay.
But then this, I mean, fitness is constant across all the individuals of the population A, isn't it? So why are we writing then Ri then? It should have been simple
Okay.
R.
Okay, if I means in the population, if I choose randomly one individual, so you can think like that. This you can think like that. So you can think like that, that in principle everyone could reproduce. So in one step, how much offspring everyone could bring in the population, that will be I n type individual, that will reproduce with the rate reproduction rate r. So IR plus how much b type individual reproducing, that is n minus I into r. So that many into 1, it should be fitness of the b type individual. So that is the total number of, in principle, that many, if I allow everyone to reproduce, that many offspring will be there in a one step in the population. Now we don't allow that many individual are taking birth in one step. We just want to make sure that only one individual is taking a birth. So and we just want to know that what is the probability that one step only one a type individual reproduces. So out of these, what is the probability of choosing one a type individual, a type newborn in a type individual, that probability will be Ri by total number IR plus 1 into n minus I. So out of this many offspring, I just want to pick only one offspring which is A type.
Which is, oh, now I understood. Yeah, so it is Ri stands for R multiplied by I, and it is not a subscript or anything else.
Yeah.
It is R multiplied by
Yes.
I. Okay, okay.
Then basically, so basically this is mean that, so I just want to only one individual to reproduce. What is the probability of that? So this is the probability that only one A type individual uh, is there in a one step. Now similarly you can write the probability of reproduction of a new B type individual. So that will be n minus I into 1. So I don't write that, Ri plus n minus I. So that is there. Now we know the reproduction rate, but when the reproduction will happen only if I take only A type individual, and if one individual reproduces. So suppose one A type individual reproduces in the population, then I have to make sure that I have to eliminate one randomly individual from the population. That then only the total number of individual in the population will remain same. So that means, what is the probability that our population state will continuously go from I to I minus 1? Excuse me. So that will be that in my population the number of A type individual reduces by 1. That means one B type individual is take birth at the population. So what is the probability of taking birth? N minus I by R minus I plus N minus R. Not only that, we have to eliminate. If we eliminate one B type individual, then there will be no change, because one B type individual, new B type individual come and we replace one old B type individual. So total number of B type individual will remain same. But in this process, one B type individual will increase. That means one A type individual has to be decreased. So that's why we have to eliminate a A type individual from the population. And what is the probability of eliminating an A type individual? That will be I by n. And now the reverse process, we have to increase our one A type individual. That means one A type individual has to born, and one B type individual has to die in this process. And what will be the probability that population will remain in the same state? That is nothing but 1 minus, it is not going to in the I minus state, and it is not going to either I plus state, I plus 1 state, then the population will remain in the same state. So this is the probabilities. Now here you see, this is the death rate, this is the death rate of A, and this is the birth rate of B. Yeah. So
No, no, it's clear to me. Yeah, I understood this.
now if this is the death rate and birth rate, then we can go back here, and we have already studied if for general birth rate death rate what will be the process. So if general birth rate is alpha and general death rate is beta I, we know that from this calculation we know what will be my what will be the fixation probability. Fixation probability will be can be written in terms of gamma k, and this gamma k is what? This gamma k, let me go there, go back there. What is this gamma k? This gamma I is nothing but the beta I by alpha I. And what does the beta I means? That beta I means nothing but what is the death rate of the individual, of the A type individual, when there is only I individual present, I A type individual present, and alpha I is the birth rate when only I A type individual present. So that we know from here, then we have to calculate gamma k, that will be beta, sorry, gamma I, that will be beta I by alpha I. And what is the beta I by alpha I here? That is n minus I by Ri plus n minus I into I by n, and alpha I by alpha I means n by n minus I into R I plus n minus I by Ri. So you see that these ni cancel, these n cancel, this is cancelled, this and this cancel, only things is left is 1 by R, and gamma I means 1 by R. And it gamma I, you see one important result here, gamma I does not depend on the birth rate, death rate by birth rate of A type individual, does not depend on how much A type individual is present in the population. So that is basically constant and 1 by R. And it makes sense because if the reproduction rate or the fitness of R is larger than 1, okay, is not larger than 1, if is okay, that this is birth rate and death rate. So if the birth rate is larger than 1, that means this gamma I should be less than 1. That is the thing. So that means it increased at it multiplied in the on a higher rate, then gamma I should be less than 1. So that is the thing. Now we have to calculate what is the fixation probability. So now we'll go back in the previous problem. What was the main problem with the deterministic dynamics? Not problem, what the deterministic dynamics tells us. So no matter from which ever state we are start, we always reach to the fixed point x equal to 1, and x equal to 1 corresponding to all n, all A type state, all A type state. So our deterministic dynamics suggests that with whatever initial condition maybe you choose, deterministic dynamics always says that at the end of the day all the individual will become A type. But similar same problem, now I want to see what is the probability that if in the initially in my population there was I initially I number of A type individuals, individual present, then what will be the probability, what will be the probability that at t tends to infinity, or at if I wait long enough, then these we will see that this all I type will it will asymptotically, or not asymptotically, will reaches to the absorbing state all A. So what is the probability, what is the probability that from this I A type individual the population becomes all N type? That means what is the probability of xi that from all I, from I number of A type individuals, in the long run the whole population will become all N. So it should, we know the expression, this is, what will be that? So what is the xi? It is 1 plus, this is 1 plus, okay, this is 1 plus summation of j equal to 1 to I minus 1 pi I k equal to 1 to j gamma k by 1 plus summation of j equal to 1 to n minus 1 equal to k equal to 1 to j gamma k. Let me calculate, because these gamma k, these are easy to calculate because these gamma k are now a constant number. So here gamma k is 1 by r. Now what this k equal to 1 to j gamma k means, that will be gamma 1, gamma 2, gamma 3, and up to gamma j, and since all gammas are same 1 by r, that means it will be 1 by r to the power j. So this is 1 by r to the power j. Is it clear up to now?
Yes, yes, it is clear. But then I have one query here, that so we considered the reproduction rate of this A species as R, and the other one as equals to 1.
Yeah.
However, it should have been more general if the, like say we could have taken it something like say RA and RB kind of the thing, because assuming that the species B is having a constant reproduction rate, I mean is not that, is not that general.
Okay, you are telling that it is instead of RA, and here RB should be written there.
Yes, yes. So
So
then it will make more sense, and it would be interesting to see that what would be that probability wherein, after some period of the time, only species A are remaining in the pool and B have disappeared.
okay, and I will say that nothing will change. This, instead this gamma k, here you will find uh, if you place RA, obviously let me write it here. If I suppose here you are saying RA, this is no, this is RB, this is RB, this is RA, this is RB, right? Now you just divide it by RB with every RA, RB, RB, and this will be disappear, and you take RA by RB is equal to 1, A, RA by RB is equal to R, and you will see the same result is appearing, no change at all.
Yes, 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 yes.
So,
Fine.
so
Not
you,
the same, but then there would be some difference, because when in the n minus I and then RB by RA, so it would be something,
no,
some difference would appear, or
no,
isn't it?
no, you see, let's do it, let's do it here, let's do it here. So here then this is the reproduction of B, so here RB should come, and this is the reproduction of A, RA should become, and this is here in place of 1, this should be RB come. Now just divided by RB, so it will become here R by RB, it will become automatically 1, and now take RA by RB is R, so this will be RA by RB equal to R, so this is remain same, and the here again, here again you will find it, here you again find it, this is RA, this is RA, and this should be RB, Now again I will divide by RB everywhere. RB, this RA by RB, this RB by RB. So RB by RB equal to 1, and this will be R, and again in upper side RA by RB. So that will be again 1.
RB by RA is equal to 1 by R.
Yeah.
So then something would remain. Something would remain.
Okay. Let
Yes.
me
Yes.
let me go through the process. uh, exactly. So let me pi to I minus 1, it should be R B by n minus I by R A I plus R B n minus I into I by n. Now what I will do, I will divide by RB. I RA by RB I plus n minus I by n. And the similar P I 2I plus 1, that will be RAI by RAI plus RB n minus I into I by n. Sorry, is n minus I by n. Now you divide it by RB again. So RB I will be 1. Oh, sorry, this will be RB RA by RB I plus n minus I will be n minus I by n. Now what we have take? We have taken RA by RB. So here RA by RB equal to R. So that means RI by RI plus n minus I into n minus I by n. Here RA by RB is exactly equal to R. So this is the same.
Yes. Yes. Yes.
So
Same
nothing will
result.
change. Nothing will change.
Yes. 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 Yes.
So that is the case. Nothing will change. Every result will be remain same. So that's it. So that's why it doesn't matter. Okay. Then let us go back to the formula, that whatever. Okay, let us go back. Where was we? That here, what is the probability that xi, that from I many a individuals will reach to the state I equal to 1. So I equal to n. Sorry, I equal to n. So for that I have to solve these equations, or not equation solve. We have solved, and this is the closed form equation, and we just want to, is there any we can reduce this form. So that's why we are looking for. So first we see that this multiplication of the jth term will come 1 by r to the power j. So this summation, what it will become, so 1 plus only upper term. So summation first term will become j equal to 1, so 1 by r, then second term become 1 by r square, and at the last term it will become 1 by r to the power I minus 1, and it is a GP series. And what will be the result of the GP series? It will be only I many terms here, so 1 by r to the power I by 1 by 1 minus r. So this is the thing. And in the this the lower is exactly similar to the upper, only the limit is to the n minus 1. So in place of this much, I will get a series like this, and it will goes up to 1 by r to the power n minus 1, and this is again a GP series, and result will be simple 1 by r to the power n and 1 minus 1 by r. Now what we have to do for xi, we have to, xi is nothing but 1 minus 1 by ri by 1 minus 1 by r divided by 1 minus 1 by r to the power n by 1 minus 1 by r. So you will get it like that, 1 minus 1 by ri by 1 minus 1 over r to the power n. So is it clear? So what is the probability that if initially in the population there is I many a individual, at t infinity, that means if I wait enough, that I many individual will automatically become n many individual, that many I many individual will take whole population. What is the probability of that? That probability of I minus Ri by 1 minus R to the power n. Is it clear?
Yes, 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 yes.
Now this is called now what is the fixation probability? If only one individual there, one a type individual there, for one a type individual, what is the probability that one a type individual will take over the whole population? That means I equal to x a equal to, this is 1. So from one individual, what is the probability that it will take over the whole population? That probability is 1 by 1 r by 1 minus r to the power n. Now similarly we can calculate what is the probability that b type individual will fix it. That is nothing but from one b type individual to, what is the probability that one b type individual will take over the or let me, this is slightly trickier, so let me talk about it little. So what is the probability that one b type individual will take over the whole population? So that means we need one b type individual, means n minus 1 a type individual, 1 minus n a type individual, 1 minus n a type individual. Now if the population is in this state, so there are all and only one b type individual, so this population either can go to this side, that all individual become red because there are only two observing set, so all individual become red, or this could go in this limit that all population will become this blue. So we know what is the probability. Suppose this is our a, these alls are a, these alls are a, and these guys are b, these are the b, and these are the a. So we know that what is the probability that from I many individual will take over the whole population. That probability is nothing but xi. So if, what is the probability that x n minus a many individual will take over the whole population? That probability is nothing but x n minus 1. Then what is the probability that it will not go to this observing state, it will go to this observing state? That is nothing but 1 minus the negation of this 1 minus x n minus 1. So that means, and 1 minus x minus n is nothing but, it is the probability that one b type individual take over the whole population. So that means here rho b is nothing but 1 minus x n minus 1. Is it clear?
Yes,
So
yes.
let me write that expression. So this will be 1 minus, and what will be the x n minus 1? So in place of I have to replace n minus 1. So 1 minus 1 by r to the power n minus 1 by 1 minus 1 by r to the power n. So this will be 1 minus 1 over r to the power n minus 1 plus 1 by r to the power n minus 1 by 1 minus r to the power n. So this is 1 over r to the power n minus n minus 1 over r to the power n by 1 minus 1 over r to the power n. Now if, okay, let me do it. So let this will be r to the power n, and this side r minus 1, and this will be r to the power n minus 1 by r to the power n. Now this will be r minus 1 by r to the power n minus 1. So this is the result. So this will be, or r minus 1 by r to the power n minus 1. This is the fixation probability of b type. Now this is, now let us calculate one important result. Now let's go back to the infinitely large limit, because we know a known result that in the this from this equation tells us if the population will be large, then from deterministic dynamics we know that the population should go from the deterministic view to all a state with probability, with certainty, that means with probability 1, because the fitness is larger than b if r greater than 1. Now suppose we are in the limit r greater than 1, we this is the case, this is the case, then what will be the fixation probability at n tends to infinity? So limit n tends to infinity, 1 minus 1 by r, 1 by r to the power n, and since n tends to infinity, that means 1 by r, and since r greater than 1, that means 1 by r to the power n should goes to 0. That means this limit will give you 1 by 1 minus r. Now you see there is a problem of there is a problem is coming. This is not a problem, this is the this is the different from what we expect from our deterministic view. The stochastic view gives us something different result. So it shows us that in spite of that n tends to infinity limit, if r is greater than 1, there is a still a probability that it is not certainly 1, that rho a is, the fixation probability of rho a is not equal to 1 but is lesser than 1. But our deterministic view, this is from the stochastic view says that in the infinite population it is not the case. Even though the fitness of the a type individuals is larger than the b type individuals, the fixation probability is not 1. That means it is not the case always a type individual will go to the all a type individual case. There is a probability, but the deterministic case says it should always be deterministic.
So this actually, this conclusion is not that clear.
Okay.
So can you summarize the conclusion here? That in the
Which
deterministic case, all the A's will become one. I mean,
huh,
all the entire population will become of A's only.
huh,
However, in the second case, what is happening that the entire population is not becoming of the type A only. However, there would be some probability.
huh. Exactly. The probability is,
So what is
probability
that?
is
I
not
mean, I
1.
cannot understand.
So in deterministic view, whatever you are saying, that always with certainty, with probability 1, whatever the frequency, it doesn't matter. So the population will hits x equal to all a state. One a individual always takes over the whole population. It is the deterministic view. That means with probability 1, that means if I comes from the deterministic view, the probability of takes over the whole population by a is 1. but
Yes.
but from the deterministic from the stochastic calculation, from the birth death process, we see that it is not the case. In the stochastic limit, the fixation probability is not 1 but it is lesser than 1. It is 1 minus 1 by r. So that suggests that there is still a probability that the population will not converge to all a state, it could go to all b state, although
Oh,
the
I see.
fitness of the b is lesser than the fitness of the a.
Okay. So, do we have? I mean, this is a general question.
Hmm.
So, do we have some use cases wherein an entity
Hmm.
which is at the verge of extinction,
Hmm.
and only very few individuals are remaining of that species,
Hmm.
again, I mean, could survive and then result into it could, survive into the majority kind of a thing.
Uh, Now, for the experimental purpose or for the observation purpose, it is not possible to actually see, because the evolution is, means whatever you are seeing, whatever is asking, it is a right question to ask. But this is very simple theoretical tool, and I don't know means there is an example. Means I don't know there is an example of this kind of thing is happening. This is only a theoretical tool to say minimally what could happen if the thing is that kind of thing.
Yes, yes. I asked this question because many species got extinct.
Hmm.
I mean, during the evolution,
Hmm.
and I never heard that the species which are at the verge of the extinct
Hmm.
could survive later on. I mean, I don't know why. Maybe there might be some examples. I'm
No,
not.
in principle, you can. I don't know the example, but in principle, people actually do this kind of evolutionary experiment. So you can do this kind of experiment. So whatever you do, but there is not a constant. Oh, there may be constant selection. Maybe one bacteria is. So in a population, in some finite population of bacteria, large kind of sub a type of bacteria, you just replace one b type of bacteria. Now you see there will be some probability that at the end of the day the b type of bacteria will takes over the whole population of a type of individuals. So that could happen, but exact probability with which probability that b type of individual take over the whole population of a type of finite a type of individual, that cannot be captured by these quantities, because this is are very simplistic.
Yes, yes, yes. I understood. Yeah.
But in the in the evolutionary sense, if you just want to see, means that is actually not possible, which one are, maybe there are in the verge of extinction, and from there they are evolved. So that kind of example I don't know, means I never heard of that kind of example. Maybe I will search for it, and if I find some example, I will tell you in the next class.
Sure, sure. Thanks. Yeah.
There is a case now. Let's. This is the one question. Now let's see some numerical things. Not numerical. So suppose A has a 100% advantage over B. That means the R is actually 2. Then what will be the friction probability? If it is 100% advantageous over B, then what is the fitness? What is the fixation probability? That will be 1 by 1 minus R. That will be 1 minus half. That will be 0.5. So that means if it is 100% advantageous, then also the probability of fixation is very low. Now, if suppose it is for a mutant which is just slightly larger than A is has a 1% advantageous relative to R. That means R is equal to only 1.01. So that much only. Then what will be the rho? What will be the friction quality? It will, if you calculate it, you will get it is very less. That is 0.016. And if suppose that in the similar manner, if it is only 1% advantageous disadvantageous, then what will be the probability of selection? So that can you calculate. So this is the 1% of advantageous. Now let, if it is 1% of disadvantageous, that means R is 0.99. Then what will be the what will be the fixation probability? That will be rho equal to 0.0058. Now another question we want to ask here. So this question is, so we can ask one question. So we can ask, how often must a mutant with relative fitness R arises before it has a probability half of taking whole population? So that means at means what is the number of times a mutant should occur in the population so that the fixation probability of that type of mutant is equal to half. So I am saying the number of times, suppose a mutant comes number of times n n number of times a mutant came in the population. So mutant came in the population means suppose there are all B type individuals are present there. Now some A type individual came, and what is the fixation probability? That fixation probability may be rho. Then what is the probability that it cannot fix it? That is actually 1 minus rho. Now if it comes n times, what is the probability that not fix it? That is 1 minus rho n. It is the not fix it for n times. Now what will be the probability that maybe in one of the time it will fix it? That is nothing but the negation of this. Negation of this will be, it will at least one time at the one population it will fix it. That probability is 1 by 1 to the power n. Now the question is, what is the this n that it should become half? Now it is very simple, that will be 1 minus rho to the power n, that will become half, and n should become minus log 2 by log 1 minus 2. Now let's see, if suppose consider a population size 100, a mutant with fitness relative fitness r, so fitness advantage r equal to 2 comes in the population. Now if r equal to 2, then what will be its rho? Rho will be 0.5. Then what will be the number of times it has to occur in the population to become the chance of the fixation become half? That number will be minus log 2, and it is also, since it is half, log 1 minus half. Rho is for 2 is half, so this will become 1. So with relative fitness 2, if it comes only once, then its chance is half. Now the same question if I ask for slightly r equal to 1.1, you will find that number is increasing exponentially, so it will become 7 times. Now, and in place of this, if I say r is 1%, r is only 1% or 10% disadvantageous, that means r is 0.9, what is the number of 7? You will find the number of n will be, so 234 comma 861 times. So that many times a type individual has to means a mutant should occur in the population. If its fitness is lesser only 10%, that many times it should occur, then it will have a chance, half chance, that it will it will fix it. So that is that is the thing that is showed by here. Now if you have any question, then you can ask me, or I can proceed to the next section, the rate of evolution.
So by and large, this is clear to me. Yeah.
Okay. So, and it makes sense if some mutant came whose fitness is slightly less than, then that means that mutant has to come many times to become fixed in the population. Now let's see the rate of evolution, and this will be the last thing that we'll do in the today's class. The rate of evolution. Now we want to ask that what is the rate of evolution. Now suppose mu is the now let's see that fixation probability in it is like a mutation. So in a population of whole population of n minus b type individuals, one A type individuals occur by mutation. So there was a B type individuals, by mutation, by error, it produced a B type individual. Oh, A type individual. So these are B, these are B, these are B, this is B. Now this A type individual came in the population because of mutation. Now suppose this rate of mutation is mu or u. The rate of mutation, rate of mutation is rate of mutation is mu. Now with 1 minus mu probability there will be no mutation, and with probability mu, so now our, let me write, now the process become that B type individual will reproduce a B type individual with probability 1 minus mu, because no mutation is happening. Now one B type individual can produce one A type individual with rate mu. So this is the mutation rate. Now if I ask, if this is the mutation rate, what is the, means, and if there are n individual are reproducing in the population, what will be the rate of mutation? That is actually, if n number of individuals are reproducing at a time, then total mutation rate should be n mu. Total mutation rate should be, this is the mutation rate of one individual, and if n individual are reproducing, what will be the mutation rate? That is n individuals mutation rate will be basically n multiplied by mu. Now this is the total probability that in a population, if n individuals are reproducing, then in the population suddenly one mutant come with what probability? With probability n mu in a once time step. And if one mutant came in the population, what is the probability? And for the simplicity we think that if one mutant came, no other mutation actually happening in the population, only one mutation came, so only one mutation came in the population with probability n mu. Now what will be the probability that this mutant will fixate in the population? That probability again is rho. Rho is the fixation probability. Only one mutation came in the population. What is the probability of mutation? That mutation will fixate. That will be rho. So what will be the rate of evolution then? Rate of evolution means the rate at which we will see that all B type individual will shift to all A type individual is, what is the rate of that? If I ask what is the rate of evolution, means what is the rate of that all B type individual will automatically go to all A type individual. That process will occur if in the population one mutation occur randomly A, that the probability of that is n mu, and the probability that this A type individual will takes over the whole population, that probability is rho. So that means it is rho into n mu. Is it clear?
Yes, yes. But then what this row is, the row is the same as the previous one or
Yeah,
something else?
previous one. This is the friction probability. Rho is the friction
Okay.
probability of same. So rho. Now if I think that rho is neutral, that there is no advantageous selection is there, means no fitness difference is there, so only neutral mutation, that A does not have any selection benefit, then what will be the value of rho? That value will be nothing but rho equal to 1 by n, because we have previously we have done the calculation. I know that if the two individuals, there is no fitness difference between two individuals, then there then the fixation probability should become 1 by n. This fixation probability should become 1 by n, because everyone has equal chance to fix it. So this row will become 1 by n and 1 by n into mu. So that means that with neutral uh, with neutral drift, you can see means they, here I am assuming there is from this to this, we are assuming no fitness difference between mutant A and non-mutant B. So no advantageous mutant came, and then the neutral deal will take place, and the probability of fixed is 1 by n, and you will find that the rate of evolution is mu. So the rate of evolution is same as the rate of the mutation, and the rate of neutral evolution, since this no selection is going on, so the rate of neutral evolution is actually the rate of mutation. And you see, this is the thing that is what is happening in the world, means it is happening in the nature, because if you uh, find in terms of fitness differences, the most species this are there, there will be no phylogenetic difference. Phylogenetic means nothing but if you compare the DNA sequence, you will find no that much advantageous gene is present, that is present for suppose for the genetic sequence of humans and the chimpanzees are not that much different, and you could not say that the chimpanzee's fitness is much more than the human fitness, because chimpanzees is also present in the environment and humans is also present in the this environment. So it may be the case, the mutation from the chimpanzees, it may be the case, the the mutation from the chimpanzees to human is homo sapiens is a neutral mutation, and because of neutral dip in two habitat, two individual, two type of species, in two habitat, two types of species spontaneously fixed in one type of habitat, homo sapiens maybe fixed, and that's why we see the homo sapiens is there, and chimpanzees is also there. It is not that homo sapiens the chimpanzees is extinct. So that is the called the neutral evolution, and it is argued that, means in many thing you will argue, it will be the argument of that, that neutral evolution is the reason for most of the species. So there is a heated controversy between the supporters of the opponent of neutral theory of evolution and the natural selection. There are two things. Natural selection means the mutation should have the mutant, if the mutant have some advantage in terms of fitness, then only the selection will select that mutant. But since you see, if we assume the mutation is nothing but the error happening in the DNA when reproducing, then the happening error in DNA is very less probable, because the DNA replication is done by a very optimized process, and that has been optimized through from this many years, these million years of evolution, and optimize the process. So you you can think like that, that the mutation rate of mutation is very low, if, and the since the mutation rate is very low, it is, even if mutation occurs, that mutation should be the neutral mutation, and the probability of occurring some drastically advantageous mutant is very less. So that means some group of natural selection, in natural selection says the difference of the species that we are seeing in the world, that may be because of this neutral dip, and another group is saying no, this is not the case. The case should be the, there would be some advantageous mutant that is selected, and that is called the adaptation. They may be adapt to that environment, and since the adaptation requires some advantageous mutation who can adapt and in those environment better than the other. This is the one group of individuals, and other group of individuals says that no, other group of evolutionists say that no, that is not the case. There is no difference between their fitness. Only the genetic drift or this neutral drift select one species, and in the other habitat they select other species. And you see that the resolution of this controversy is not so difficult. So if you see the evolution from the molecular version, so molecule are means this DNA version. So DNA are replicating, and because of the replication of DNA, a new offspring produces. And if you see through this, the genetic drift or genetic version of this stochastic version or this neutral drift is much more compatible. And neutrality is a good assumption for building mathematical tools to calculate the phylogenetic relationship among the species, because it is very easy to calculate. So certainly at some point there will be very less probability of mutation, and because of the mutation some advantageous gene could came, and that could invade the whole population, but the probability of that thing is very small. And we will see this is called the weak selection. That means almost means larger amount of evolution is happening because of this mutation business and this neutral dip, and very small amount of evolution is happening because of the selection, and because of the frequency dependent selection and uh, frequency dependent different of the fitness. So in the next class, so let stop this class in up to now. Now I will discuss in the next class that how we will see that naturally this argument says that we have to assume this kind of fitness. This is dependent, this comes from game theory, this came from evolutionary EGT, this comes from evolutionary game theory. This says that the evolution is because of fitness differences, and fitness, and this part is because of the neutral drift. And the selection is weak means if we go to this w tends to 0 limit, then we will say the selection is very weak. And we will find that this w if instead of fa x we will place this whole term in the replicated dynamics, the outcome will not change from the replicated dynamics, but this weak selection limit, since is the larger part of neutral drift, this weak selection limit, you will see that that will create that will give a lot of results that is not similar to the what we expect from the deterministic replicated equations. So that's it for the today's class. So if you have any question you can ask me.
Yes, so I have a little query here
Okay.
that we are I mean creating we are I mean developing equations
Hmm.
to understand a phenomena.
Hmm.
But then I mean modelers I mean what strategy modelers used to use
Hmm.
instead of using the equations like say system dynamics or the agent based modeling.
Hmm.
I mean those modeling phenomena where they do not develop the exact equations, but then they create some kind of the model and then they change the population and then the different parameters to study that how the evolution is taking place. So how effective those tools are?
Okay, agent based tools. Now you see this evolutionary game theory is a still a it's not well developed tool, means not well, not I am saying well developed, means it is a thing where people are there is no experimental evidence is that much experiment has been done in evolution, so now people have started to do experiments. So one of thing is that, and second thing is that the evolutionary game theory up to now is means the large amount of the work is only theoretical work. So people have some theoretical questions. So one of the question is that why that so much species is there speciations, and why the cooperation in the population is stable there. So these are the theoretical questions. To tackle these theoretical questions, people use the agent-based modeling and many other kinds of modeling. You can see that stochastic game, people use the stochastic game to tackle the question, what is the reason behind the evolution of cooperation. People use the agent based model to see that what is the reason behind the cooperation among the agents. If and people also use that here we say whatever say in a one space, we are not saying the variation of space. We only account for the time variation, and we in our mind we don't say here, but we in our mind keep that things that everything is happening in a one position, so there is no special variation is there. So people also study if maybe the special variation occur in the population. So it is not the case that all A type individual present there here only in the position and all B type individuals present there only here. So there will be spatial variation also be there. So people used to study the spatial variation also in these things. So this
Okay,
is the
okay.
things.
And to yeah. And tomorrow's class would be at the same time?
Yeah, at the same time. And the tomorrow's class we will discuss two things. One is that what is if I include in this whole picture. Up to now this is neutral evolution. Now if I include the frequency dependent selection, that will came automatically from the game theoretic evolutionary game theory, and what it will change, and how we have to change the definition, or how we have to modify the definition of ESS to tackle this finite population case.
Okay, okay,
Okay.
sure.
Okay.
Thank you so much.
Okay. Then
Bye.
bye.